Ben West and Matt Hartz would like to showcase the usefulness of Lagrangian mechanics using an elastic pendulum as an example. As can be seen, a fairly simple experimental setup can produce a very complex system. As the mass extends the spring, it increases the length of the pendulum, which increases its time period. This makes the system actually very difficult to model. This is a diagram of the system, where L0 is the rest length of the spring if it wasn't swinging, and x is the amount that the spring is extended by, with theta being the angle from the equilibrium position of the pendulum. Before we can explain further, we need to go into some of the background maths. In this case, if a variable has a dot on top of it, that is just notation for the time derivative. 2 dots is a second order derivative, and so on. Next are unit vectors, which you should have seen before, but are just vectors of magnitude 1 that go in the direction of the x, y, and z axes and are labelled I hat, j hat, and k hat. Finally, partial derivatives. This is where you take the derivative of a function that contains two variables, but you're only interested in how that function changes with respect to one of those variables. So you treat all the other variables as if they were just constants. It is that simple. If you use the Newtonian method, you end up doing a lot of very complicated vector maths, and all you produce at the end is one single differential equation that actually turns out to be very difficult to solve. In this case, presented as line 8.
There is an easier method for finding out the equations of motion of the system. This is using the Euler-Lagrange equation. This equation is nice, as it uses energies instead of vectors like Newtonian physics does. The symbol q in the equation signifies a generalized coordinate. Generalized coordinate is just a coordinate in which we don't really mind about what direction it uses, we only care about the magnitude of it. In the system we're using, we are only using the generalized coordinates of extension and angle.
In this case, there are two energies present, the kinetic energy and the potential energy. The kinetic energy is quite simple. It's the kinetic energy along the direction of the spring and the energy involved in the swinging motion of the pendulum. The potential energy is simply given by gravitational potential energy and Hooke's law. When you take potential energy away from the kinetic energy, you end up with an equation called the Lagrangian of the system. This has been given the symbol L and is found on line 3.
Now let's try and find out the equations of motion of this system. We will first use the general coordinate of displacement.
Let's leverage what we know about partial derivatives. If we're looking for delta L over delta x, we treat all the terms in L that don't have an x in them as constant. As you know, when you take the derivative of a constant, it just becomes 0, so you can ignore all those terms. Once you know that, you just have a series of very simple derivatives to take care of. This is because you can treat each term in an equation separately when you are taking derivatives. This is exemplified when we look at delta L by delta x dot, because there's only one term with an x dot in it. Everything else is 0, so we just end up with mx dot. The time derivative of this is easy. The time derivative of velocity is just acceleration, or in this case, x dot goes to x double dot. Now we just substitute what we know into the Euler-Lagrange equation for this coordinate, and we find a differential equation comes out the other side. This differential equation gives us information about the relationship between the extension of the spring and the angle of the pendulum. Now we just need to do the same thing for theta. In L, the Lagrangian, there's only one term with theta in it, not a theta dot. We're only interested in thetas. So delta L by delta theta is very simple to solve with a little bit of trigonometry. Similarly, there's only one theta dot term in the Lagrangian, so delta L by delta theta is, again, very easy to find. The time derivative of this is a little more complex, because we also have to take the time derivative of x, because we know that that is also going to vary with time. All we need now is to substitute what we know into the Euler-Lagrange equation, and now we have a differential equation in terms of theta. Fantastic. We've now produced our two equations of motion. One tells us how the spring extends and contracts over time, and the other tells us how the whole thing swings. And this system of connected differential equations is going to be much easier to solve than the vector-based one that we found earlier with the Newtonian solution. If you solve those differential equations and add some initial conditions, you can produce a simulation of the system. The phase plane diagrams for simple pendulums or mass spring systems are ellipses, so it's very interesting to see these still repeating patterns, but they're much more complex.
This shows us the power of Lagrangian mechanics, as using a few short, simple steps, it allows us to model a very complicated system into fairly simple differential terms.